Hi, I'm Andrew. I'm your TA for ME166. This is going to be the first in a short series of videos to help you review for the midterm. This one will be on stress and strain as tensors. So where these come from, we start with a body, which I'll draw here, and say that body is under some forces at the ends. What stress and strain are going to tell us is we take a little element inside that body, and we want to see what the forces on that are, and that'll give us the stresses. And we want to see how this little element deforms, and that'll be the strains. So for example, for the stresses, say that this is our element, and say that we have a coordinate system over here. We'll call this x and y. So this element is going to feel some forces in the x direction, and so we'll call those on the x face and in the x direction. We'll call those sigma xx. It's also going to feel forces over here on the y face and in the y direction. So we'll call those sigma yy. And then also we might have some shear stresses involved. So say that we have a shear stress on the x face in the y direction, like this. That would be sigma xy. And likewise, if we have a force on the y face in the x direction, that'll be sigma yx. And so at this point, we need to finish balancing these out so it doesn't rotate. So we'll add these other ones out here, and we're done. So now we have these four components, and we can write them all as a matrix. So we'll write it like this. Sigma yx, sigma xy, sigma yy. All right, great. So we have them all in a matrix, and the question is, what can we do with it now? So if we have sigma ij, so we're trying to pull out a different component, what this is going to tell us is that's the force in the I face and in the j direction, right? And so for example, if we wanted to, if we had our tensor sigma and we wanted to pull out the forces on the x face, what we could do is we could multiply it from the left by a vector 1, 0. So when we do that, multiply this by our tensor over here, we get a vector sigma xx and sigma xy. And so both of these are the two forces on the x face. So if you look up here, it's the sigma xx on the x face and the sigma xy, the shear stress on the x face. And the same way, if we wanted to pull out the y components of the forces, we could multiply it from the, or if we wanted to pull out forces in the y direction, rather. So we'll multiply it from the right to get the forces in the direction. So say I'll multiply it by 0, 1. So what that's going to get us is a column vector this time, sigma xy and sigma yy. So this is the force on the x face in the y direction here, and the force on the y face in the y direction up here. So basically what a tensor is an object, so we'll call it sigma, that can be multiplied from the left and from the right by vectors pointing in a direction. And when you do that, you pull out one of the components of the stress. So a lot of times when you look up tensors, people will say things like it's invariant to coordinate transforms, or there's a whole lot of definitions out there. But this is what they're all basically saying. It's saying it's an object. It has, in this case, dimensions. So stress has dimensions of megapascals or gigapascals or whatever. And then these unit vectors only have direction. They don't have magnitude. So you can pull out the component of the force of the tensor in any direction using those unit vectors and on any face. So that's the idea behind tensors. One more thing I want to talk about here is about the definition of shear strain as a tensor. So it's slightly different from what you would have done in ME15. Um, so in that class, you would have, for example, started out with a box, and you would have put it under some shear stress, and it would have deformed like this, right? And you would go over here, and you would call this angle gamma, you would call that the shear strain, right? Now, the problem with this, if you look at it, is this box right now is not in equilibrium. It's going to start rotating to the right. So what we actually need is a box like this. One that has those forces, but then also has these other shear components that put it in equilibrium. And so this box is actually not going to deform this way. It's going to turn into like a diamond shape. So for example, I'll make my little diamond here. Say that this is our diamond. Erase a couple of those. So what we're going to have here, this is, and this is in our coordinate system, this is x, and this is y. So this here is how much we've shear strained the x direction into the y direction. So this is shear strain xy, and this one up here is shear strain yx. And you'll notice what this ends up being is that each one of these is 1/2 of gamma, so that we end up having gamma equals 2 epsilon xy, and that's 2 epsilon yx. So this is called the engineering shear strain. And then these two are both called the tensorial. So I just wanted to point that out so that there's no confusion. One last thing. So we want to be able to express these tensors in different coordinate systems. That's what I had talked about. So imagine if instead of drawing this particular box, say we had drawn one that was at an angle like this. And so maybe that box, if we draw it over here again, looks something like this. And let's say that that has a coordinate system. I'm going to draw them all in red. So we'll say the red x goes that way, and the red y goes that way. Let me move this up a bit so that it's not out of view. Okay, so in this one, we're going to have different components of the stress, right? And so how can we transform the stress tensor from here to here? And the answer to that is you can either start using your linear algebra or you can use Moore's circle. And so the next video I'm going to do, which is very optional, is I'm going to show you where Moore's circle comes from and how to use it.